sunumunu da hani ekrana hazırlayıp belki de belki yok. Devlet farklı bu gelebilir. Böyle devlete şeye ait. Evet. Evet. Kumandaydı hocam.
Bu şekilde bunu böyle konuşmak için hocam bu şekilde tamam şöyle vereyim çok anlamında yerlerde gidiyor tam bir şey başka bir çok da bir şey benim hocam bu her selam hocam biraz
Bir de konuşmalarını dikkatine alabilir miyim? Tamam. Sunumda yazdık. Hocam, devam edelim. Alttaki kurtulman değil mi? Evet. Right. Good morning. Welcome to last day session of the ICMATSE24. Today's first speech from the Dr. ANKARA from Boğaziçi University, Istanbul. Osman Sefa got his PhD from University of the Illinois at Urbana-Champaign, the Department of the Materials Science and Engineering. He is an assistant professor now, mechanical engineering at Boğaziçi University. His research interests are solar energy and machine based optimization. Please. Thank you, Dr. Atesh, for the nice introduction. So, good morning and welcome back for the last session. I'm also the session chair, so hopefully I'll do the administrative stuff. So the first one is mine, and this is still a work in progress, in which we're trying to work on Bayesian optimization, trying to optimize material systems with both continuous variables as well as discrete variables. And in this project, an undergraduate student from the Istanbul Technical University in Material Science Department is also working with me. So now, let's look at some examples of some optimization problems in materials domain. So, for example, the first one is maybe we might have composite bullets that synthesized using broadcasting and would like to maximize its electrical conductivity. Or it could be a flow synthesized silver nanoparticle, and the objective is to maximize absorbance across a spectrum range. Or it could be thin perovskite that's used commonly now, getting more common in solar cells and etc. But it has some stability issues. So maybe the idea is during this synthesis via spin coating, what can we do? What knobs to tune basically to be able to have a more stable perovskite structure? Or it could be from additive manufacturing domain, and the idea is this 3D printed structure is not as mechanically tough as its both counterpart, right? So what can we do? Maybe it could be increasing the viscosity of the ink, could be the speed, it could be some sort of post-processing that we should do to have more tougher structure, or it could be it's just optimizing the shape. But hopefully, like what these optimization in materials domain is very wide, and it has lots of applications. The problem is we cannot just try all sorts of variables, right? We have a finite amount of time and resources, so it's not possible to come up with every single variable combination. So what we would like to do is closed loop feedback while we optimize this structure. Turns out there are like three main methods that's used in materials science domain. The first one is local optimization method. These tend to be fast and gives result, but the main problem is, as the name suggests, it's a local optimization. So it gives an optimized result, but it doesn't guarantee that it's the lowest possible. It's not the global minimum or globally optimal. The second one, and it's called stochastic optimization. And maybe you've heard some of them. These are called like particle swarm optimization or differential evolution. There are some like B algorithms, for example, based on this. They work fine, but they tend to converge slower. So the third one is model-based method. And the most common model-based method is Bayesian optimization. So the idea is we have some objective function, okay, but it has no closed form. What that means is we cannot just write a mathematical equation. If we can, then we can just take its derivative to get the optimum, right? But for these, we cannot. So for example, let's say there was a nice talk yesterday from solar cell, thin film solar cell application. And in that one, you have back contacts, front contacts. You might have front buffers. You have P layer and N layer. And they all come from different materials and they have different thicknesses, right? But in this one, these are all your inputs, right? So the materials and their thicknesses are your inputs. And the output could be open circuit voltage, or it could be the efficiency, for example. So you have inputs and you have outputs, but you cannot just write them mathematically. You can run simulations to get the output, or you could actually go ahead and experimentally make the solar cell and measure its efficiency, for example. Okay? So Bayesian optimization is used when you cannot just write a mathematical equation. And it works by initially having some initial experiments. Okay? Let's say I randomly choose 10 solar cells and simulate them. By random, I mean the materials and their thickness. Okay? And then the model, we generate a model that we call a surrogate model. And then the idea is the surrogate model tries to approximate the actual model, but we don't know the shape of the model. And then through its acquisition function, it tells us what should be the next input to do, what should be the next simulation, or should be the next experiment. So based on the first 10, it tells you what should be the 11 inputs. And then you do the experiment and place them in the model. So now it updates the model based on 11 inputs, not 10. And keep on iterating until you're either satisfied with the result, or maybe you say, okay, stop after 300 iterations and get the result. This is how it works. There are different types of acquisition functions, and also there are different ways to model, to come up with those surrogate models. The most common is Gaussian process. This is what I do also. But you could use like random forest. You could use artificial neural networks. There's a huge flexibility. But even for this Bayesian optimization, the thing is, what people try to usually do is you have a specific material set. Okay, so you initially come up with the materials, and then you just optimize the thickness. Okay, because thickness is a continuous variable and it fits nicely into this Bayesian optimization. But what happens if you would like to co-optimize both the materials and their thickness, for example? And this is, for example, the focus of my talk today. And in here, you cannot just place a discrete variable inside the equation, right? Because you cannot just do it just doesn't fit nicely. So you in this case, for example, you have continuous variables. It could be particle sizes, it could be, I don't know, like solvent concentration, it could be thicknesses, whatever it might be, but you also have discrete variables. So these could be, let's say I have 20 materials in my database, what should come in as the third layer? Or it could also be a binary variable. So let's say you're synthesizing an element for a superconductor, and you're trying to see the effect of binder. So that could be a binary. So there's a binder or there's no binder. So you could also include binary variables here. So the idea is that with some tricks, it's possible to introduce these discrete variables. And in that case, if you have both discrete and continuous, you just call it mixed rate. And the idea is, so you have some function that you'd like to maximize, right? So, but you don't know where you are. So you're somewhere in here, let's say you're at this point, and you're just trying to search the area with it, as well as explore outer areas. And wherever you get close, basically after 300 iterations, that's your global outcome. In here, this is how the surrogate model fits in. So these points, greenish points, are your exact results. And then the model just is trying to come up with the rest of the blue lines, and the purple shadows are just your uncertainty. That's how it works. And then you could use it for your simulations or experiments. But that's the idea. So as you see, this is quite general and can be used. And in my talk today, I just wanted to focus on solar selective absorbers. And just in this slide, let me explain what they are. They're basically trying to use the energy from sun to heat a fluid. So these are like pipes that we have a heat transfer fluid. Okay, initially it's cold, but since these pipes are located on top of parabolic troughs, so basically you have a focused sunlight about in here where you can place the pipeline. So as the cold fluid flows across, it gets hot, right? And by using a heat exchanger, it's possible that you generate electricity by having a turbine in here. And in the meantime, the fluid gets cold again, so it can flow across here, gets heated up, and keep on recycled basically. That's what a solar absorber is. It kind of looks like this. Within a glass envelope, you have the solar selective absorber, and inside heat transfer flows. The idea is it absorbs in the solar irradiance range, which is around between 300 to 2500 nanometers. So the idea is the reflectance is ideally zero, so the absorbance is 100%. And then beyond 2.5, where there's no basically sunlight, it reflects everything. So the absorbance is zero. And that's something to do with anything that I'm going to talk about in the next slide. And these are just some common ways of visualizing. So you could have like some photonic or plasmonic structures. You could have a single layer, but this is hard to come up with just a single layer that does this. So you rather use like multiple layers of metals or dielectric to come up with a structure that mostly absorbs in this region, but doesn't absorb at all locally in this region. So and this is an example. For example, if you see this is reflectance. So, and this is roughly 2.5 microns, right? So in here, reflectance is very low. So the absorbance is very high because see, there's no transmission. So this is constant, a big constant, and there's also constant over there. So the transmittance is zero. So we could just measure the reflectance, and the rest must be absorbed. Right? So the reflectance is very low in this region, and it's very high in this region. So why we should have as high reflectance as possible? Because all the objects that has a temperature above 0 Kelvin emit light. And that's how thermal cameras work, for example. If you have a fever, for example, your body temperature is above 37 Celsius, so you emit at a different wavelength, and also if the emittance from body also increases in power, and which is shown. So that gets picked up. So remember, I have a pipe that's quite hot, right? So I do not want to lose any heat due to radiative heat transfer. That's the idea. And turns out this is a function of emissivity as well as temperature. So we do not want to give up from temperature. So we should be able to reduce emissivity. And emissivity is just equal to absorption by Q cross thermal law. And since we don't have transmission, you could just say absorption or emissivity of just 1 minus. So that's why we should have as low emissivity values as possible, between 2.5 to 15 microns. And turns out there are also material systems for low infrared emissivity, and it might have like thermal camouflage or heat efficiency problems. And actually, this is something that I'm also working as another project. Like we're trying to come up with nanoparticle synthesis that we can introduce for thermal camouflage or heat efficiency. So now, when we try to bring it back together, the idea of this talk is hopefully it's now understandable that Bayesian optimization can be instrumental in material science domain. But pretty much all the studies that have been reported in the literature focuses on just tuning the continuous variable. Okay, but especially that comes from computer science domains, that now it's also possible to include mixed spaces like discrete variables, categorical variables, binary variables inside the Bayesian optimization. So the question is, can we apply mixed space Bayesian optimization to materials domain? And my focus of today's talk is just solver selective absorber, but hopefully now it's evident that it can be applied to all sources. So now specifically the question is, can we optimize the material selection and synthesis at the same time, rather than just focusing on a single material system and trying to optimize their individual components. That's the whole idea. So now let's revisit this. This would be the ideal case where we do not have any reflectance, and then we have 100% reflectance of 2.5 microns. And in this study, I just chose a copper substrate and 5 layers on top, and these are the 5 layers, and we just chose these thickness ranges. So it works by basically, for example, okay, layer 1, let's choose a material from a database and choose a thickness, and do the same thing for 2, 3, 4, and 5, and simulate the whole structure. Okay? These are the material databases. We only chose 10. The idea is we should be able to get optical constants for the material. So, and that's not, it doesn't exist for every single material. And also, these are mostly kind of materials that we could deposit using a PVD method, such as magnetron spot, for example. In this case, again, we have some initial experiments for simulation, and then we generate a model. And the acquisition function search through the material space. These are, in my case, material selection and their thickness values, and simulate. These simulations could be rigorous coupled wave analysis, or it could be transfer methods method, and then goes in a loop and then choose best combination after a while. So in this case, for example, the trick to introduce the Bayesian optimization to include mixed variables was reparameterizing optimization problem by introducing the discrete probability distribution over a random variable, some Z Before, people were trying to parameterize continuously over the discrete parameters directly, but that has some problems with it. So there is a library that's open source that was developed by Facebook developers. So in that case, I used their library. And another thing is the sunlight is not does not come in a single wavelength, as we know, and also so it spans around 300 to 2500 nanometers. But as you see, it's not comparable, right? It's more the spectrum is radiance is tied around 500-600 nanometers, and it basically falls. And there are also some sharp falls in this. And I mentioned I use transfer matrix method. It's a method to study the propagation of electromagnetic waves through some simple tests, for example. That it doesn't take diffraction into account. So we do not have these are just single layer forms. We do not have any features on like crossbars or any other thing. These are just flat layers. Okay. So we know Fresnel equations are derived to get reflection and transmission at the single interface, right? And in transfer matrix method, if we have more than a single interface, they can just be multiplied. This is how the transfer matrix method goes. So you generate a matrix at each interface, and you multiply those matrices to get a one final matrix, and that just depends on that just connects your input to the final output, and the output is transmission or reflection. And if I know both, I just get the absorption, right? So there's no diffraction or any other secondary effect of going from this up. So we can just get reflectance and transmittance, and it's also angle and polarization sensitive. In our case, we just simulate normal incidence, so it comes in, and if it's normal incidence, also S&P polarized results will be the same. So this is what we have been doing, and this is the result. So we optimized two separate structures. In the first one, the idea is we do not take this AM 1.5G spectrum into account. So we say that, and we optimize by taking these values at every 25 nanometers in absorption band. So we start from 300, 300, 325, 350 until 2500. We have roughly 80 something points, and we get the average at each point to have a mean absorption. And we do the same thing for emissivity between 2500 and 14 microns. But now, I believe we do it at every 100 nanometers. Again, we get emissivity values at each, I believe it's 114 points, and then we take its mean to get a single value. So in here, this is mean absorbance, which means we do these simulations, okay, 300 to 2500. We have in total 89 points, and we just take the average to have the mean absorbance. And turns out this simulation, the optimization results give us, we have 7 nanometers titanium, and then we have 30 nanometers of germanium, 40 nanometers of titanium, 25 nanometers of silicon, and 195 nanometers of copper. And then below this one, we have again copper substrate. Okay? And this is how it looks like. So this is absorbed. Okay? The mean absorptance between 0.3 microns to 2.5 microns, there are 82%. And from 2.5 to 14 microns, it's roughly around 9%. So we can say that it's mostly reflective, but it should be, and it's reflective is very low. We could do better, of course, but this is based on the material selection, and also thickness, wavelength, and layer numbers. This is what we got. And secondly, we optimize the weight absorbance. And in this case, what we did was we get an absorbance number, and then we multiply this number by 2, the spectral irradiance from AN1.5G, which means that it tends to optimize better in this range compared to in this range, right? So this is the high. This is the most valuable part in the weighted absorbance case. In the other one, it doesn't really matter. So that's why in here we have a huge, like 90+% absorbance in this region, because this is the most valuable region. This is the region where we have the most compound. And turns out it's 7 nanometers of zinc oxide, 40 nanometers of iron oxide. So in this case, for example, all layers 2, 3, and 4 turns out to be iron oxide, because we do not constrain. We do not say that it should be only a material in only a single layer. It's possible to add additional constraints, but we do not need to do that. So this one is actually even more advantageous, because on top of substrate we only have 3 types of materials, so it will be done easier in, for example, in real life, right? If you have access to a sputtering machine, you will just 3 rows, for example. So, and it turns out it's weighted absorbance is around 80%, and emissivity, as you see, it's mostly coming from here anyways, and emissivity is around 4%. It's a bit high in here, but when you average between 2.5 and 14, it's 4.4%. The reason we stop at 14 micrometers is because most of the values that we got from the database offer to, like 214 microns or so. If we can get more values, we could extend. But also, when you look at this black body spectrum, what is, and if this fluid is hot enough, okay, let's say it's at 1000 Kelvin, above 10 microns, we do not have much, right? So most of emittance is around in this region. So maybe it's also 14 microns good enough for power. And we also we haven't done the weighted emittance, but if we know the exact temperature, then it's also possible to improve in that one. So with this one, I'd like to summarize by telling that the idea is mixed space Bayesian optimization works with some tricks, and it can be applied to materials engineering domain. And the topic, the application that I chose was solar selective absorbers. They have the idea is to have unity absorbance between 300 and 500 nanometers, and pretty much zero absorptance beyond. And of course, we could increase the performance by introducing more materials in the database, maybe increasing the number of layers or the thickness ranges. But the idea is it can be applied to many problems in the materials domain. And like a side project we're working on basically show that we could actually come up with an optimized structure of dielectric metal core shell nanoparticles for low emissivity applications. The criteria here is just that we should have the simulation of the problem. If we can simulate it, and if we have 10, for example, 10 results, then we could tell this model can fit those 10 conditions and tell us that what should be the 11th experiment, 11th iteration of the simulation. And if we do not have the simulation, just the experimental work, that can also be applied. So let's say you have 10 experimental results of, let's say you're trying to increase conductivity. Based on that one, the model can actually model those 10 conditions and tell you what to try on your 11th iteration, basically. With this one, I'd like to thank you for your attention, and I'd like to thank Twitter for the funding so that was these internal ones, and I can take any questions you might have.
Thank you for this beautiful presentations. As an industrial engineer, I know emissivity what it is, but I don't know what it exactly by this presentation. So can you please explain it more by saying what is emissivity, work on your project?
Sure.
Thank you.
Okay. So let's go to, let's see. So we know, and you said, if an object is at above 0 Kelvin, it emits light, right? And this is what we call radiant heat transfer. So it transfers the heat, and heat is a type of energy, right? It transfers the energy to the outer environment. And that's why, for example, you say you're a civil engineer, so industrial, okay, I'm sorry. But for example, it has applications in space, or it has applications in civil engineering, for example, for like heat insulation and other things. In here, what we wanted to do is, we do not want to lose any energy due to radiation, transferring those energy, basically. That's what, because, and this will get quite hot in a couple of hundred Celsius degrees. So this is not just water, so that's good. So as it flows through, we do not want that energy to emit outside. So we want it to be kept inside, and so that here is still hot, as hot as possible, so that we could generate electricity. That's the reason we want very low emissivity after this region. So there's no light to collect in this region. It's just purely, so this is gain, this is loss, pretty much. That's how we can do that.
So thank you very much for a really interesting presentation. As an experiment, so I'm thinking a point of view or approach is, this is really very good for us to start with simulation, and then we go actually to do the experiment. So this is the same question for your approach. You start with the simulation, and then you make this kind of telling us what we expect to see sometimes. Did you apply it for real life examples, so then we can compare this absorption statistics with something in real life? Because what we are seeing actually, for instance, another parameters that might also affect the absorption, like the roughness of these layers. Okay, so instead of just having full layer without not taking care about the environment around, maybe it will be difficult to follow up this kind of approach.
Okay. Thank you. Yeah, nice question. Thank you. So now, ideally, yes, we want the simulation to approximate the real life as much as possible, and there's still some things that are missing. And if we can realize that, then we could introduce back in the simulation. That's possible. But what is also possible that maybe you're working on a system and it's just the simulation will not make sense, or maybe there is no available simulation. Then you could do the complete experimental route as well. And there are some papers and some, especially this comes from like chemistry people, that they try to optimize the synthesis. Okay, no simulation at all, but they can synthesize molecules very quickly. So what they do is that they have 20 molecules that they synthesize, and each 20 molecule has some differing variables, solvent, temperature, time, whatever that might be. But they still want to do the optimization, and they do not know which route to go. And then they have a very similar approach, Bayesian optimization, that basically models whatever they have, like 28 experimental results, right? So it can model and give you the 21st iteration of experimental results. That's also done, and there were some like open source libraries that people can use. That's mostly coming from my chemistry. That explains well.
Because now you open my mind for this kind of theoretical physics regarding semi-chemical rainbow deposition, because usually we are introducing different gases in the mind, we are fabricating the environments. So we can control these numbers, the reaction, as well as the amount of the gases are coming in. So that actually will help us to know exactly the parameters that we are, well, say the best parameters. So yeah, this is very helpful. Thank you very much.
Yeah, you're welcome. And like to add on what you said is in this one I have not talked about, but this is roughly the first iteration of the model that's been. And we could push this further. So what people have been doing is, so for example, in my case, what I've been trying to do is maximize the absorption, in visible region or near air region, and minimize the absorption after 2.5 microns. Right? So there's only one thing that I'm trying to optimize, but there's also multi-objective optimization. So in this case, maybe you're trying to optimize, okay, this one, but also let's say each stack is, each material has a different cost point, right? So let's say, what is the best possible stack that's also the cheapest, for example. And in that case, maybe you have some solution that's very high in performance but very costly. So you can tune it basically. So that's called multi-objective optimization. And also the other thing is, and this might also be useful, is okay, optimize this. And in my case, for example, so this is what we have. Right? Maybe layer number one, its thickness and material selection is much more important than layer number four, maybe. And in my case, it doesn't also do anything. So there is this thing called, and it's quite popular for the past couple of years, explainable AI, meaning that we have this black box neural networks. You gave it some input and it gave you some output, but it doesn't know it's doing, but it cannot explain. So that's where explainable AI comes in. And that's some like extension that we'd like to do in the future, saying that okay, this is the best case, but like your layer number two material selection is the most important. And afterwards comes the, let's say, layer number one thickness. That's because it could also act as anti-reflection layer. I mean, we could take this like to all sorts of we could expand upon it for both applications and also make it more robust. Just expand it. Any more questions? Right. So now I'm done. We have more speakers session, and next up is do we have Dr. Edney or Edin?
Osman Hocam. Osman Hocam. Meryem Bozkaya invite, please.
Okay, now we have Meryem Bozkaya in next up, and her talk's title is Synthesis of Two-Dimensional Hexagonal Boron Nitride on Food Substrates via Low Pressure Chemical Label Deposition Method. I invite you, Dr. Bozkaya, for your presentation.
My presentation. My presentation. Go. Okay, okay. My presentation title, sorry, uh, three, okay. My presentation title is, Principles of Two-Dimensional Hexagonal Boron Lights, on core substrate via low chemical, I'm sorry, I'm quite excited. Via low pressure CVD method. Okay. The extract is the high quality synthesis of hexagonal boron nitride on core substrate without exposure to non-catalytic effect is crucial for the use in optoelectronic applications such as quantum emitters or UV observation or UV deep UV photodetector, etc. Here are two-dimensional hexagonal boron nitride was successfully synthesized on quartz substrate, and the growth time examined on grown hexagonal boron nitride effect. According to the result of X-ray photoelectron spectroscopy, it was found that the growth time plays a significant role in the synthesis of high quality HPN. Okay, what is the hexagonal boron nitride? Hexagonal boron nitride is aka white graphene, is a 3,5 compound possessing a similar honeycomb lattice structure to graphene, but with a different band gap energy. While the graphene has no band gap, hexagonal boron nitride has a wide energy band gap. And to enable energy band gap depends on the number of layers. Such a graphene analog has drawn intense attention in recent years due to high thermal conductivity, superior optical properties, high mechanical strength, chemical stability, and elevated temperature, and atomically flat surface, which is so important because traditional substrates like silicon, aluminum nitride, or gallium nitride is high for energy and carrier trapped, and so the optoelectronic device can be degraded its performance and properties. So this is a method of hexagonal boron nitride can be realized two routes, top-down approach, including mechanical gravity, liquid exfoliation, chemical weathering, etc., and bottom-up approach, such as chemical vapor deposition, vapor deposition, pyrolysis, molecular beam epitaxy, etc. But top-down approach is some of drawbacks, especially limited size because hexagonal boron nitride power 30 microns, and liquid exfoliation or mechanical exfoliation just limited 30 microns. So on bottom-up approach, physical vapor deposition or PLD or MBE method is so expensive and precision process. But chemical vapor deposition is most promising due to large scale related to low flows, control over deposition, and scalable synthesis. Chemical vapor deposition actually to the two-dimensional material, if it's one to large scale product, most preferred method. Chemical vapor deposition process chemical vapor, the process, the parameters of chemical vapor deposition is so important to synthesis two-dimensional materials, such as growth time, growth temperature, type of carrier gas, type of precursors, type of substrate, amount of precursors, and type of pressure, such as atmospheric pressure, chemical vapor deposition, or low pressure chemical vapor deposition is so important to synthesis two-dimensional materials, because the low pressure, at low pressure, the atoms slowly than the atmospheric pressure emission, and so the atoms less scattering, and two-dimensional domains more easy. Okay. Precursor type also so important, because hexagonal boron nitride, two element compounds, boron and nitrogen, and boron and nitrogen stoichiometric ratio is so important, 101. Boron chlorure, boron trichlorure, and ammonia. Diboron and ammonia is the gas precursor, but so toxic and so dangerous. Borazine is the liquid precursor, but borazine as liquid is not stable. The borazine just liquid helium zone or chamber inside. Yes, okay, then stable. So ammonia boron is solid precursor and non-toxic, stable in air, decomposition in low temperature. Also, the most important parameter in CVD method in synthesis two-dimensional material, substrate type, catalytic substrate and non-catalytic substrate, the use CVD method. Catalytic substrate is transition metal, such as copper, gold, silver, platinum, and catalytic substrate is when the two-dimensional material is domained, the formation energy is decreased because of the catalytic metal, catalytic effect, but non-catalytic materials is not degrade formation energy, and the more energy is necessary to synthesize two-dimensional materials on dielectric substrate, which is the more energy is can supply elevated temperature or low pressure. So, okay, my, sorry, my presentation or my study is hexagonal boron nitride two-dimensional non-catalytic substrate, because most of the applications for such CVD grown hexagonal boron nitride to need transfer process the other substrate, other applied substrate, such as silicon or solar cell or etc. And the transfer process is more complicated, and so um, so mm, so it has drawbacks such as the material, when the transfer process the other target substrate, the materials, two-dimensional materials, can be cracked, can be fault, or can be have some defects, polymer defects, because the transfer process is need to polymer coated PMMA, such as PMMA or PVA, and then target two-dimensional materials when transferred, the polymer coating is H with the acetone, and this process can be contained in polymer defects. So direct deposition method on quartz, silicon, alumina, sapphire, or aluminum nitride, gallium nitride. This is so advantageous because it's no necessary transfer process, and then the materials, two-dimensional materials, is properties not degrade. Experimental method, ammonia boron is solid precursor, and alumina both to inlet because of the CVD system is the CVD system that my studies is rely, and ammonia boron is directly quartz tube after the loaded into the quartz substrate, and ammonia boron was decomposed with the help of heating belt, and heating belt is 60 centigrade degrees and heated, and after that the ammonia boron is decomposed, and hexagonal boron nitride source is with the help of carrier gas in reach the quartz substrate, and low pressure in the experimental session approximately 1 torr millibar and less. Okay, then hexagonal boron nitride synthesis completed. The system is cooled in air emission, This is the left down picture is the hexagonal boron nitride grown quartz substrate actually, and then the first hexagonal boron nitride structure analyzes X-ray spectroscopy, X-ray photoelectron spectroscopy. Then after that, the structure analysis and optical layer analysis with the Raman spectroscopy. It's analyzed. Okay, I'm so sorry. I'm so excited. Then when the expert analysis is examined, 15 minutes. The three samples is the expert spectroscopy in the figure, and growth time. The growth time was chosen 15 minutes, 13 minutes, and 1 hour. It found that the expert spectroscopy, according to the expert spectroscopy, 13 minutes from to growth time was increased from to 15 minutes to from 15 minutes to 1 hour. BMB bound is more BMB bond peak is more high and more thin, and 15 minutes sample the expert spectroscopy in obtained P and O bond peak was obtained because boron is the tendency of oxygen, and while growth time while the growth time is was decreased, oxygen is eliminated, and with the help of carrier gases, argon or and hydrogen. And so boron and Pb bonds is more suitable bonds. It examines the Raman spectroscopy of hexagonal boron nitride. Raman sheet is 1373. This is volume is hexagonal boron nitride. Actually, two-dimensional hexagonal boron nitride of Raman sheet is that volume. Bulk hexagonal boron nitride, the Raman sheet is not 73, 65, because hexagonal boron nitride has a layer interaction, and hexagonal boron nitride layer is decreased. Layer attraction is decreased, and Raman sheet is more high. And PR spectroscopy is examined because it's PL spectroscopy actually band gap energy obtained of hexagonal boron nitride more sufficiently, but in my laboratory in my laboratory on PL spectroscopy, unfortunately, minimum 250 nanometers, and hexagonal boron nitride band gap luminescence is less low. Just so the hexagonal boron nitride of PL spectroscopy is more defects, more obtained, more obtains more defects, and the peaks actually hexagonal boron nitride defects of hexagonal boron nitride, especially it is 300 nanometers is boron vacancies hexagonal boron nitride. And when the growth time was high, decreased defects in structure was decreased during the long growth time. In conclusion, in synthesis of two-dimensional hexagonal boron nitride on a dielectric substrate with other catalytic effect, growth time plays a crucial role in achieving a high-quality structure. Thank you for your attention. I'm sorry again, I'm so excited. I was excited because I'm not enough practice in speaking English. Any questions?
So thank you very much. Please relax, everything is okay and fine. Thank you very much.
Thank you.
Yes. I'm just wondering about the final result. The layer. Is it a single layer of hexagonal boron nitride that you achieved? And did you check it in the Brahmans or any confirmation? This is the first question.
Actually, it's not just Raman spectroscopy result is not just yet monolayer hexagonal boron nitride is not, because supporting characterization, especially AFM, atomic force microscope, or transmission electron microscope is necessary in the sample is monolayer. But unfortunately, AFM spectroscopy characterization is not reached in my lab and my project. But actually, I won the last month in scholarship for in Texas A&M University in USA, and my doctoral thesis. Actually, this is my doctoral thesis, but my experimentalist stopped, and because due to a scholarship in Texas A&M University, and there I continue to experimental, and finally healthy characterization with the sample characterization, I hope. Finally, this necessary air command them or can.
Shall allow you to.
I know.
Just the last question regarding the transferring this layer. Because you said maybe you're gonna use it and then transmission it from microscope, so you need to transfer it
Yes,
from the quartz, the substrate is quartz. This is the quartz substrate, yeah?
yes, quite substrate.
Yeah, it's like, is it like graphene, like using PMMA, so then you can transfer it? Or is it something different because you use non-catalytic approach here?
Actually, the same transfer process, again, polymetal metacrillate, but different chemical solution in quartz aging for quartz.
Did you try it yourself?
I'm sorry,
Did you try it? Did you transfer it by yourself?
just graphene synthesis,
Okay.
graphene, not hexagonal worm like that.
Thank you.
I'd like to thank the speaker and also congratulate for the funding she received. Hopefully, that will be a nice research time for her. And so, who do we have next? Do we have Dr. Daniel? Okay. So, he's coming next. Oh, she's coming next. I'm sorry. The names aren't given, so I'm sorry. But the name of the talk is investigation of the spring-back behavior of double-phase steel sheets in the V-banding concept. Follow it goes.
Hello everyone, my name is Ela Düzenli. I am a master degree student at Gazi University and my supervisor is Professor Dr. Hakan Gürül. The title of my presentation is the investigation of the spring-back behavior of fluid-phase sheets in the V-banding process. This is my outline. First, motivation. What is the banding process? V-banding, spring-back, fluid-phase systems, experiment preparation, conclusions, and then finally references. Motivation. There are many studies in the literature that examine the spring-back behavior of different materials. However, there is no study found that compares spring-back values of the three different materials such as DP600, DP800, and DP1000 in V-banding process. The aim of this study is to examine the spring-back behavior of the DP600, 800, and 1000 steels in V-banding process through experiments and to find the reasons for the differences in this behavior. What is the banding process? The banding process is a method of permanently shaping a material by applying force. V-banding is a method that is widely used in shaping metal sheets, especially in process using sheet metal or metal sheet plate. Spring-back is an unavoidable situation. V-banding process is a forming method that allows metal sheets to bend at a specific angle. This process is usually carried out using a V-shaped die and punch. Bending processes are widely used in many industries, from automotive manufacturing to home appliances, and from aerospace to electronics. The spring-back is the tendency of a material to partially return to its original shape after the force used in shaping is removed. There are many factors that affect spring back, such as material, sheet thickness, bending angle, bending radius, and temperature. In this study, analysis was used to find the results for calculating spring back. The main reason for spring back is the elastic deformation of the material. Spring back is a common issue in manufacturing process and can affect product quality. Therefore, various methods are used to understand and prevent spring back. Dual fast steel sheet is a special type of steel with a microstructure containing two different crystal structures. These two phases are used ferrite and martensite. This is ferrite, this is martensite. Ferrite gives steel softness and formability, while martensite provides high strength. BP600 is easier to form because it contains less martensite, but BP1000 is harder to form because it contains more martensite. Dual phase steel sheets are widely used in many industries due to their high strength and good formability. They are used in many fields such as the automotive industry, construction sector, machinery manufacturing, and household appliances. An example of dual phase steel used in a vehicle is shown in the figure. In the experiment parameters, the die width was set to 125 mm and the punch width to 65 mm. The die corner radius and punch corner radius were taken as variables are 3, 4, and 5. The punch speed was set to 1 mm per second. EPS 600, 800, and 1000 materials were used. The sheet metal thickness were determined at three different values: P 1 mm, 1.5 mm, and 2 mm. Three different dual-phase steel materials were used in the experiment. To transfer these steel materials into analysis program, tensile tests were first performed. Engineering stress strain curves were obtained from this test. Then, Turun curves were obtained from this tensile test. These curves were transferred to analysis program and analyses were performed. The left figure shows the part shape after forming and spring back in 60 V bending, 60-degree V bending, while the right figure shows it for 90 degrees. After the bending process, spring back behavior was analyzed. Tables show spring back values three different steel materials, BP 600, BP 800, and BP 1000 at 60 degree and 90 degree V bending with sheet thicknesses of P1, 1.5, and 2 millimeters and bending radius of R3, R4, and R5. Effect of material and sheet thickness on spring back. The following spring back values have been obtained for bending angles of 60 degree and 90 degree at the bending radius R3 for three materials. It has been observed that as the material thickness increases, the spring back values also increase for both bending angles. Among the material tests, BP600 exhibited the lowest spring back values, while DP800 demonstrate higher values and DP1000 yielded the highest spring band. Effect of bending angle on spring back. Spring back values obtained for the DP600 material at a bending radius of R3 for bending angles of 60 degree and 90 degree are present in the graph below. As shown in the figure, the block line represents 19 degrees and the red line represents 60 degrees. The experiments show that the amount of spring back increases linearly with increased bending angle. Effect of bend radius on spring back. The spring back values obtained for the CP600 material at bending radius are 3, 4, and 5 for bending angle of 60 degree and 90 degree are presented in the graph below. As seen in the figure, the black line represents R5, the red ones represent R4, and the green ones represent R3. As seen in the figure, for all sheet thickness, the lowest spring back values appear where the radius is the largest, like in R5. Accordingly, as the radius increases, the spring back decreases. Small radius causes more plastic deformation in the material and increases the spring back. On the other hand, large die radius decreases the plastic deformation and decreases the spring back. It was found that the spring back decreases with increased die radius. As the yield strength of the material increases, the spring back values also increases. It was observed that the spring back decreases as the sheet thickness increases. As the bending radius increases, the spring back decreases. The lowest spring back value was 2.6 degree for DP600 material, 2 mm sheet thicknesses, and R5 mm punch radius. The highest spring back value was 12 degree for 1000 material, 1 mm sheet thickness, and R3 mm punch radius. References. Thank you for attention.
Thank you for the presentation. Are there any questions?
First of all, I'm trying to congratulate you for the good presentation and valuable information being informed. From your result, it seems to me, depending on the plastic deformation in the bending region, the spring bank's value has changed. Because of plastic deformation, how much or how percentage spring back can take place? Is there any measurement or observation?
Yes. 60 degrees, DP600 and sheet thickness is each sheet thickness is 1 millimeter and various band radius R3, R4, R5. If sheet thickness is the same, band radius is increased spring values are decreased.
Okay. Thank you.
Thank you.
Thank you for the presentation. So now, let's see who's next. Do we have Dr. Aksoy?
Yes, I'm here. My name is ICMATSE24, and I will presentation with the gas metal arc weldability of strength 700 MC steel with flux core filler metal. If it's possible, I will presentation this paper.
Okay, okay, yes, now we have the next speaker, and I believe this is the last one, but the paper name, gas metal arc weldability of strength 700 MC steel with flux core filler metal. And yeah, we can see the slides, and you can present whenever you're ready.
Okay, I think you can see my screen. And I will make the full screen right now. Wait a minute, please. I think there is some problem with my computer. Wait a minute, please. So sorry. Can you see my screen right now?
Yes, we can still see it.
Okay, thank you. This presentation title is Gas Metal Arc Weldability of Strength 700 MC Steel with Flux Core with Filler Metal. And we have four researchers. First of all, Serhat Aksoy, our master students. Second one is our supervisor, Professor Dr. Ramazan Kaçar. Third one, and me, and Samet Nohutcu. And last one is Associate Professor Hayriye Ertek Emre. And we are working in Karabük University graduating from right now from Karabük. And first of all, introduction in gas metal arc weldability of strength 700 steel. And strength 700 MC steel is high strength, low alloy steel, and are characterized by their high strength and formability, as well as good weldability. These steels, so high strength, low alloy steels, using in manufacture of truck body frames, dump trucks, automotive, train, crane, and mining machinery. And so many places we can use these steels, and also good shape, and also their strength is also high. And weldability of these steels is important to produce vehicle, crane, and other industry, also transportation industries. The main problem is in welding of these steels of loss of superior mechanical properties of the base metal due to the localized softening due to the thermal cycling of we are using to welding, so it produced to some thermal cycling. For this reason, research on the welding of these steels has been concentrated in this welding, this field actually. And some studies in the literature with gas metal arc weldability of these steels, but flux core gas metal arc weldability application are some limited. So we use flux core filler metal in this research. And also after this welding, the mechanical properties of joints were determined by tensile test, hardness measurement, formability, and XRD, SEM, and microstructures investigation. Experimental material and method, and we use strength 700 MC steel plate tray, and approximately 100, 500, and 5 millimeter thickness for material, and material strength, yield strength approximately 700, and tensile strength maximum 950 megapascal, and elongation approximately 1000. Preparation of the test specimens before joining welding process. We opened the weld groove 60-degree V shape, and we used the water-cooled gas metal arc weldability machine, and also we used the filler metal 1.2 millimeter flux core, and for joining parameters approximately 140 ampere current intensity, and 250 millimeter and slash 1 minute to feed rate. Mechanical specimen preparation. After the welding, we cut the plate with CNC laser, and we machined this specimen with CNC milling machine for good surface clean. And after this, we prepared the metallurgical specimen preparation, and we used the classical metallurgical method. We used the 5-second etching with 2% nickel on sample, and after this, we investigate with SEM and XRD measurement. Microstructural investigation of welded joint. We can see the three microstructure. First of all, is in base metal. We can see the optic microscope image, ferrite, bainite, these phases. Second one is heat affected zone, and we can see the three region: wet metal, heat affected zone, and also base metal. And we can see some coarsened grain inside the heat affected zone. And as a main problem in this investigation, we use the thermal cycling, and this thermal cycling affected to especially heat affected zone like the coarsened grain like this. And third microstructures image is wet metal, and we can see some optical image ferrite and martensite phases inside here. And we can see some EDS results, all of them, some carbon, chrome, iron, and molybdenum. We can see, for example, in churn image, we can see some percentage of carbon is very high. So this is indicates to some iron carbide, molybdenum carbide, chrome carbide, like some carbide and oxide inclusion were starting indicators of fracture. These are the results. Also confirm the structure is composed of alpha ferrite phases, and also we can see some little bit vanadium carbide and silicium oxide inside the material, especially welding area. These second phase particles like vanadium carbide and silicium oxide and other things, and also these second phase particles harder than base material matrix, and although they contribute probably great initiation and are responsible for decreased deformability. We can look at right now determination of mechanical properties of weldment. First of all, we can see the some right side the graphic, and two of them is green ones, and this is base material of strength 700 MC material, and three other one is after the weldment. So we can see weldment displacement result is lower than base material. Yes, but when we look at the left side of table of result, average of strength 700 base material yield strength approximately 750 megapascal, and tensile strength approximately 888 megapascal, and elongation is approximately 12. And right now we can see the weldment average. Weldment average of yield strength approximately 519, and also the tensile strength is very similar, 598. Sorry, 6, and approximately elongation is 5%. Yes, we can see the result is not very similar between weldment and base material, but strength of specimen welded flux core gas metal arc weldability method, yani use this method more than 2/3 of strength of base metal. So it is acceptable for strength of welding. We can see after the specimen of test, we can look the right side of the EDS analyze and send image. We can see some pits in the fracture surface image, which are indicate of ductile fracture, planar spherication, and some grains indicate that the specimen fracture with semi-ductile, semi-fracture mode. And also we can see some inside the pits, some formational observed within the pits that are beginning of fractures. And also we can see the EDS result, and we can see the easily carbon is a little bit high, more than other elements, and also iron and chrome someone, and first and third one is a little bit high, and we can see the inside also some carbide or chrome carbide, iron carbide like this produced inside these pits. Hardness measurements result and evaluation. Strength 700 MC, approximately 267 Vickers. And after this, while going to heat affected zone, a little bit high, going too high to hardness, approximately reaching 280 Vickers, and is going to, while going to weld metal, is decreased to hardness and to approximately 240 Vickers. After this, weld metal is hardness approximately 250 Vickers. We can see the right side of elemental mapping analysis of weldment, and some point we can see this carbon and iron is changing, decrease or increase. So actually this result explains to why hardness is changing to strength and base metal to weld metal. After this, we made the bending test for investigation to shaping result after development. We can see there is no crack formation, no crack, weld cap, weld bead surface, and weld root. It's very good formability, approximately 120 degree. We can see the macro view of after bed test. There is no crack formation, and formability is acceptable. General conclusion: microstructure of base metal of development predominantly composed of polyhedric ferrite, and so bainite and martens. You can see inside the some microstructure image, and also yield strength or tensile strength also acceptable is given to strength of main material to church is acceptable in welding, and also weldman hardness base metal average 207 vickers, and also when we can look to heat affected zone and welding, and approximately it's very similar, not to very big differences, so it's also acceptable for hardness. In the bending test, no crack formation was observed all three area, and it's indicate that good weldability or good shaping. There is no problem with formation. Thank you for attention.
Thank you, Dr. Noki, for the presentation. Do we have any questions? I believe we do not. Dr. Noki, thanks again for the presentation. I believe this was the last one, so I'm closing the session. And thanks for your attention again, and have a nice rest of the day. Yeah.